Okay, so like I said, today we're going to talk about time series analysis in GoldSim, and um, now some of the things that I will show you, it could be more appropriate to do it outside of GoldSim, perhaps as a pre-processing task before you start the model or you start building the model. But there are some times when it's useful to have these tools in the model itself. If you're perhaps updating the values often or something like that, then it might be more convenient to have it in the model. But a lot of times these kinds of functions can be done outside. But for those times that it's nice to have it in GoldSim, I wanted to show you. But also, there are a few things that are very convenient to do in GoldSim, and it might make more sense just to use GoldSim for it. So starting off, I want to talk about just some real basic concepts regarding the time series element. What we see here are just a few elements. These elements are containing time series data from this Excel spreadsheet, which I obtained from the water data website of USGS. You can search various locations of gauges that they have maintained data at. This one is in Washington, and they have a whole bunch of various parameters that they're monitoring at this site. They're listed here. And if you go down to the actual data, then you will see, for example, here's max temperature, min, and average temperature. These time series are are being shown down here, down where it says temperature. River flow and dissolved oxygen are also from that spreadsheet. Now, what we have in this spreadsheet are it's raw data, and you can see here there's a flag here, A, and it says up here what that means, approved. There will be some cases where it might not be approved, but worse than that, the value might be missing. They might not have recorded a value on that date where they might have with other values. And so when you just try to copy and paste this into a time series in GoldSim, GoldSim will not allow it. It will not allow you to deal with to save blank values in the tables of these time series. The reason for that is we don't know what the value should be, and we don't want to make a guess for you. And so the best approach is to first go through the data in Excel and fill in those blank values with something else. So you could put an error code like a -999 or something in here to indicate that it's not there. And that's exactly what I've done with this temperature average called temperature average raw. That means I just put some I can't remember if I put zeros or negatives. I think I put negatives in there in replace in a very large negative or very large negative number to indicate that it's missing. The other option is that you could make use of GoldSim's time series interpolation capability. So that's defined here where it says represents. And so you could say, well, I want to interpolate values that are missing. The important thing that you need to make sure that you do here is that you do not include the date time row associated with the missing value. So as an example, let's say we go down in this table here, and let's see, am I missing? Okay, here's a good example. So we're missing a value right here on 12/7/2010. So what you'd want to do is you'd want to omit this entire row. If you're gathering this data here, putting it into GoldSim, you'd want to omit this entire row, the date and the value. So an easy way to do that, instead of just going in here, right click, delete the row, that's a bad way to do it. Well, what I would suggest you do is use a pivot table. With a pivot table in Excel, here's a pivot table of that same column we were looking at. This C3, this happens to be I didn't copy over the correct column header. It's not C3, it's actually average temperature. But just imagine this as average temperature. So all you have to do when you create a pivot table is when you click inside the pivot table, over here on the right, you have some options. And we just need to take the value, the C3, that's the average temperature. You just need to move that down into the values box down here, and then also to the filters box. And then this thing called 20D, well, I should have labeled that better too, but that's the date time, this column A. So you just need to move that over to the rows column. Once that's all set up, then because you have a filter set, you can come up here to the filters and make sure you check the box, select multiple items, scroll all the way down, uncheck blank. Make sure all the rest are checked except for blank. And then when you do that, it will remove any blanks in here. And you notice these are still in order, these values. And so you can just simply copy and paste this, and it's ready to go with all of the blanks removed. And since those are removed, and also since our data is shown to be representing instantaneous interpolated, it means that we get interpolations between those points. So let me show you what that actually means. If I zoom into a place on this time history, you can see that the green is the raw data, the red is our interpolated. And so where we have removed values, so over here, when you're not missing very many points, it makes a lot of sense. It works quite well, actually. The red line is what we end up with after interpolating linearly between the points that are missing. You get to some other places where it's not so realistic, like here, where you're missing more days. But even worse, you could get to a place where you're missing a lot of data. Let me just zoom in like this. I'm holding the control key on my keyboard, by the way, to zoom. Okay, so likely this is misrepresenting, what occurred in that time right there. So this could be problematic. I think it might be better in this case here to perhaps copy from another year the values that go there, or omit this part of the time series in your model. Something like that would need to be done. Something other than a linear interpolation. But it's good to know that you have a couple of options on how you can represent time series and handle missing values. And oh, by the way, you can also see that I did use a -99, it appears, to flag any missing values. It's a good way to flag them. It makes it really pop out in your charts if you're trying to deal with that. Okay, so the next thing I want to show you is how to use reporting periods in order to calculate some seasonal statistics of your time series. Okay, so I'm going to grab that one, reporting periods. Okay, same data set, essentially, with one difference being that if you go to the simulation settings, that we have reporting steps, major and minor reporting steps set up. You can see here that our basic time step is 1 day. That's because that's what our time series records are measured, are recorded in daily increments. So we have a daily time step, but I also want to see things like what is the monthly average or the annual average, that kind of thing. It's very easy to do that if you set up reporting steps here, in addition to the basic step. Note, when you set this up, that GoldSim will, by default, save results only for the major and minor periods. So you would have to change this to say, no, I want to see it for reporting steps and also basic steps. And then select one right here to make sure it does that for every single basic step. If you want to see how GoldSim is saving the points, when it is saving values, you can click on this button up here called Show Scheduled Updates. And then it has this little key up here at the top that shows you these little characters that represent the different kinds of data that it's going to save at the different points in time. The H is your basic step value that we call the time history result, just the thing that's being saved every single day. Notice also the date, it's a date time. So we're saving these values at midnight every day. And that's because our start time is midnight. Okay, but if you scroll down, you will see we hit these points that have a little m, indicating minor reporting period. So we're going to save a value for, in this case, June, the end of June. Keep going. Here's July, etc. Eventually, we're going to get to a point where we have a capital M, probably at the end of the year. Here it is. At the end of the year, notice it reports it on midnight of January 1, but that's really the end of the year, a major reporting period. Okay, so that shows you when it's saving information. Now, when we run the model, we can look at things like comparing daily and reporting period values. To understand what we are grabbing here, well, you can look at the Y1 and Y2 axes to get an idea, but the best way is to go to the properties. And in the properties, you can see here that we have reporting period set under the time display settings. So this is an option that you'll have if you set up reporting periods. If you select reporting periods here, then you'll get the ability to, well, I should go to edit mode here so you can see this. Close that. Let me go back. Okay. So if you set reporting periods here instead of simulation time, then you'll have this ability over here in the period results drop list to choose a statistic of what you want to see seasonally. And so we want to compare daily values. So it's nice. You can pick all plot points. That will include all the daily values. In addition to that, you can look at a statistic like cumulative over the period. You can also look at average over the period. Note that if I pick cumulative, it's got different units. So on the Y1 axis, we're going to have cubic meters per second. On the Y2 axis, gigaliters. Okay, so that's how we get those values set up. Now when you run the model and you look at the results, you can see we're looking currently at monthly periods and comparing that to the daily values in red. We can switch this up here to annual and see how the annual values compare on year, and so forth. But this is not giving us necessarily statistics of each year. So, for example, this tells us the cumulative amount we see in 2014 right here. But it's kind of hard from this chart to get an idea of for example, what's the mean? What's the mean of all of these blue values, all of these annual values? What is the mean? What is the standard deviation of it? What is the 90th percentile? We can kind of look and just say, well, this must be the maximum. Here's the minimum, or maybe this one, etc. So it's kind of a visual thing, and this is useful for reports and so forth, to get a big picture idea of what's going on. But if you really wanted to get a statistic of on an annual basis, meaning put all of these annual values into a histogram, for example, you would need to do something different. And so while this has a lot of usefulness in your models, you might need a little bit more. And so to do that, I'll show you another model that you can set up similar to this. And this one is reporting period statistics. Similar model, except now what we're going to do is set the model up, the simulation settings up a little bit differently. Previously, if you might recall, we were running a historic period. We were running from 2010 to 2019, I think, or maybe 2018. Something like that. Now we can run any period we want. Let's just say we're going to do a future, some period in the future. So this is a hypothetical year that we are running. It doesn't even have to be dates here, by the way. We could just do an elapsed time model, which doesn't care about calendar. It would just run 365 days going forward. So that would be another way of doing a forecast, going into a hypothetical scenario into the future. But we're just going to assume that we're doing a hypothetical future run for next year. And we want to use historic data to represent that. We're going to make the assumption that whatever happened in the historic period of record will likely happen into the future. Some variation of the things that we saw in the past. And so with that, then we can just simply iterate over all of the years on record and see what they produce. And we do that using Monte Carlo in the case of GoldSim. So we go to the Monte Carlo tab, and I'm going to put the number of realizations in here that is equal to the number of years on record. Turns out we have 9 years on record. Not very many. It's not ideal, but that's all I have currently. So I'm going to run it for 9 realizations. Then what we need to do is we need to tell GoldSim how to sample or where to start on the first realization. So if you're kind of new to Monte Carlo simulation, just know that what we do is essentially we kind of just iterate over doing multiple simulations all at once, well, in sequence. But that when you hit run, it's going to start with realization 1 and then realization 2 and 3. And on each realization, it's like a whole new simulation. But we have the ability to modify what happens at the beginning of each subsequent realization. And we can do that by creating this constant here that's called shift year. Now it's a constant for the duration of the simulation, but it's changing on each realization. And we do that by referring to a run property called realization. So this thing increments starting at 1 on the first realization and increments forward 1 by 1 on each subsequent realization. So you can see that the expression here would start out 2011. On the next realization, it would be 2012, and so on. So knowing that, we can then put those values into our time series to do what's called time shifting of the time series data. So if you go to the time shifting properties here, you can see that we're shifting by the shift year, where on the first realization, it will grab the 2011 data, and then the 2012 data, and so on. And that's how we can make sure that all of our time series are synced. We're grabbing the same years on record for each realization using this global variable called shift year. Now that we were able to do that, we can run the model for 9 iterations, and we can look at all of the data at once. So one way to look at it is with a plot. Just trying to make this thing a more reasonable size. Okay, so this gives you an idea of, and I'm changing the instead of linear points, I'm going to change it to stair steps, just to give you an idea of that we're looking at individual months here. But now you can take a specific month, let's say June. We can take June and look at this. It's essentially a probability distribution, but you're looking at it from the top, down, from up above, looking down onto it, where the mean is this black line, well, the 50th percentile actually. But you can see here that this is the spread of where that data is in June. And so this gives you a little bit better view of possibilities of where things are on each month. All similarly, you can do that. Well, you can't do it for the years because this only runs for 1 year. So it only makes sense in this case to look at monthly there. We can do the same thing with the river flows, and oh, this looks like daily data. So this is daily. Look. Oh yeah, that's the daily data. Even though it says monthly over there, that's the daily input value. So we really want to just look at this one. Anyway, this gives you an idea of the statistics for each of the months. We can also look at this in a table view. As long as it's got the display set here to probabilities, then we can look at the min, we can look at the max, 50 percentile, 75, 95 percentile. So that, it gives you for each month, it gives you a range of possibility for what we have seen in the past, which could be useful to have. But what if we want to take that kind of information and use it as an input somewhere else in the model? Well, there are a few ways of doing that, and I'm going to show you a couple, and it requires a little bit of analysis on the time series. The one that we're going to look at next is pushing or building an array. In GoldSim, we call these vectors. Building a new vector that has all the values from the time series in it. And once it's in a vector, then you can do functions using our built-in array functions that we have. Okay, so I'm going to open another model called Array Statistics. Okay, so what this is essentially the same data again, but we need to look at how many rows of data are in this table. If you just hover over the icon, you'll see here it shows you 3,367 number of records in this time series. Okay, so if we want to convert this time series to an array, to a vector, we're going to need an array that has 3,367 rows. And actually, I think it's 3,366 actually to be accurate, because the very beginning and the end, one of those is not used. But anyway, the point is you go up here to array labels and then go to TS rows. It's just a new set I created. Just click on new set and click indexed. And then once you do that, you can then type the start index and the end index and see it goes to 3,366. So that's a pretty big array. But now that you have that, we can build an array by just referencing each row of the time series. And this is done using this equation right here. And so the equation is vector constructor. This vector constructor is a built-in function in GoldSim that will iterate over the entire array And you can do things as you walk through the array. You have to actually think of this as a compact for loop, similar to something you would see down here, where you have a for loop that says starting with row 1 of the time series and going to the size of the array, so in our case 3,366, and then increment the row 1 by 1 and do this, which is you build a new array referencing the current row and assign it to your time series at the row specified. We multiply by 1 day because the time series is date based, and so you give it a date unit and it will go to that point in time. Okay, so that's what we did, except we used the vector constructor, which is a compact version of this for loop. All right, so we go in here, and here's the equation, the vector constructor of the river flow time series, grabbing each value on each day. And then what you end up with is an array at the end. And if I run the model, we can actually look at what that array is. It looks like this. These are all the daily values. Not very useful, but you could compare all of these values with the time series. They should be the same. Okay, so with that, now we can do our we can use our built-in array functions, such as mean v, that's a built-in function, get the mean immediately, standard deviation, the min, the max, stuff like that you can get. So by putting it into a vector, it allows you to do a lot of things with it. It gives you a lot of power. You could keep going. You do a lot more things with it. But one thing I just want to make note of is this is a one-time calculation. You can do it at time 0. You don't have to walk through time to do this, to build this array. It happens immediately at time 0. Knowing that, there is no reason to recalculate that. Just do it one time and be done with it. In order to do that just one time, you have to put the whole thing into a conditional container. If you have ever run the model, notice it runs in less than 1 second. It doesn't even show anything on the clock down here. It's 0. It's so fast. But look what happens, however, if I disable the conditionality on this, just make it a regular container, and then run it. You'll see how much longer that takes. So I know it's only 1 second, but you could imagine if you had a big time series and a lot of stuff in your model, this would be a problem. So you want to make sure things like this, if it's something that's calculated immediately, there's no reason to recalculate. It's the same answer every time. So in this particular case, we want to put conditionality on this container, and then tell GoldSim to update it immediately upon activation, essentially at time 0. But then right after that, disable this time series. I'm just going to say on true, eDay is greater than 0. So after time 0, just disable the thing and don't update it anymore. And if you do that, when you run the model, you see it's very fast. So that's a good thing to do. Okay, so that's putting your time series into an array, which is useful. The next thing I want to talk about is monthly and annual totals that can be used in the model as an output. Okay, so I mentioned before how you can use reporting periods to find, for example, monthly average or annual average. Well, sometimes you need those numbers at the very beginning of your model simulation. If you need those immediately, then it probably makes more sense to do it this way, which is essentially, again, building arrays. But this time we are going to, for example, to get, the average or cumulative for a given month or year, we're going to need integrators to calculate those. That's the easiest way. I mean, okay, we could do it with just an array, and it would be more complicated. This way is pretty easy. We're leveraging GoldSim's elements to do it, and we have a model example that you can use to get this. Just copy and paste this. All you have to do is just replace the input right here into this very first element, and all the rest will be taken care of for you, as long as the number of years in your array, which by the way is up here, array labels, as long as your number of years is equal to what you have on the record in your time series record. In this case, 1948 to 2017. And I'm just going to check that in my time series. Sorry, I'm in the submodel. Here we go. In the time series, 1948 to the end of 2017, but we don't do anything in 2018. So I just want to view the results from 1948 to 2017. That means I need an array label set that has all of those years in it. So we're going to put cumulative and average values into this array label set, or into this array with these rows. And the functionality that I showed you inside of here does that. And when you run this model, you're going to get things like, well, come back all the way up here to the outside. You're going to get things like the monthly averages. So this is similar to what we saw before when we used Monte Carlo with reporting periods, except you have the values. You have the values actually at time 0. So just putting that time series in here, at time 0, we can calculate this table right here. We can have this table of values immediately available at time 0. That means we can use this going forward. For example, we could just repeat over this and say, these are my averages in my model that I want to use, something like that. You can do the same thing and get things like min and max, standard deviation, annual sums. All of that can be then brought to the outside of the submodel and used immediately. And again, the submodel, similar to what I did with the conditional container, is I set up the trigger to run the submodel. I made sure that it only happens at the very beginning, time 0. So we don't have to repeat every time. That will save a lot of time running the model. The reason it's in a submodel, though, is because it does require that this thing walks over the time series through time. Because look, if you go to the submodel and you look at time, the time tab, you'll see that it runs for the same period of time that we have in the time series. And we have to do that because we're using integrators to calculate sums and averages during the seasonal periods, the months and years. But this is a submodel, right? So it's like a model within a model. This model can run as a preprocessor at time 0 of the main model and produce these arrays immediately. Now I'm only showing one, but they're very easy to add. So right now I have the monthly average, but if you want to add another output, you just go to the interface tab, come down here to the outputs, and just pick one. Annual sums, for example. And we want to export the final values as an array. And then and don't worry about how it says mean right there. We're not doing a Monte Carlo simulation, so it doesn't matter that it's the mean. It's going to be the same regardless. But anyway, so we're going to end up with annual sums that then we can reference on the outside here and use it in the model. Okay, the next one I want to show you is doing a distribution of the values in your time series. Okay, so in this case, what we're doing is what you could do is you could take all the values in your time series. In this case, again, we have 40,000 values, over 40,000 values. This is a different time series than the one we had originally. You see, it goes all the way to 1904, so a lot of data. But you can already see immediately we have an error flag right here, -999. By default, what we would do is just put all these values into a histogram and show it in a distribution plot. And the way that you do that is that you need to set up your model to be you'd want to have it static, and then your Monte Carlo is going to run for a number of realizations that is equal to the number of records you have in the time series. And actually, it should be, to be a little bit more clear, in case you're omitting any rows in the time series, you'd actually want this to be the number of a number of days between the first date and the end date, because values that don't exist, it would just interpolate, which is probably fine. So just keep that in mind, that this number of realizations has to be the number of records, number of rows, or sorry, number of days between the start and the end date of the time series. But once you do that, then you can produce a distribution. I moved it into a submodel because it could be that you want that distribution at time 0 again. That's why I'm doing all these submodels. It's so that a lot of times you need these outputs if for the model you're running. Sometimes you don't. Sometimes it's just for presentation, and so you don't need to put it in the submodel. But if you want to have it immediately available, then you would do it this way. Okay, so now with that being said, we can run the model, and then we can go into the submodel and look at the distribution. When I look at this, you can see that it's showing up here that there's a chance you get this negative 999, which actually pulls the mean down quite a bit. So we want to screen out these error values, negative 999. Okay, how do we do that? Well, we use screening. You can use Monte Carlo screening, and to get there, you go to the properties, and you can do this with a time history element as well. There's this button called options, and this is a global thing. Okay, when you click on this, it's going to be the same exact window for any result element that you're in. And what you're able to do here is down at the bottom, you can then specify screening conditions to remove any values that you don't want to see or include in your results. And so you can do that by simply adding here and then type in a condition. And in our case, the condition would be river flow values is going to be less than 0. And I think we need units. In this case, we're using cubic feet per second. So I think that would work. And once you do that, you can uncheck the box, and this would then remove a portion of the results from your chart. And when I click OK and close, let me see. Oh, it's still checked. Did it uncheck? There we go. See how negative 99 is gone, and so yeah. So now it doesn't show it in there. So that's a way to screen out those values. And then what you can do is you can come over here to the output, the interface here, and then you can link the final value distribution, the entire distribution, as an output. Notice how it's referring to river flow values, but the output definition is here I should okay, if we're going to edit this, there you can see it better. So one of the options on exporting a final value from a Monte Carlo submodel is the distribution. I want to export the entire distribution out of the model, and that way you can then calculate, for example, the flow's standard deviation, and also in this case the mean, flow's mean. And you can calculate these things just using these built-in functions right here. They're accessible by right-clicking, going to Functions and Special, and you will see some of them down here. PDF mean, PDF standard deviation. You can also look at what is the value given a probability. So pretty powerful things you can do with statistics on all of the values of your time series. All right, the next one I want to show you is correlation. Let's say you have, for example, temperature data and dissolved oxygen data for the same point location and same time points. So, and you want to see how the two measured values correlate. And to do that, we need to look at a new model that I'm going to open here. This one here. So it's the same data we started with at the very beginning. I put that all in here. And then what you can do is do a similar calculation where you run the model for a number of realizations that is equal to the number of time points you have. And then it's just a static calculation. And you do a lookup on the time series and you get a value. And you can then use a multivariate chart to compare multiple outputs together. In our case, temperature versus DO. If I open up this chart, then you get something that looks like this. And you can see that there is a relationship, and you can even look at what the correlation is between temperature and dissolved oxygen. It says 0.9. If we have a linear correlation, then it would be quite easy actually to set up an equation that would allow us to model dissolved oxygen given temperature. So for example, what if the dissolved oxygen values are kind of spotty, hit or miss? Maybe they didn't record that as well, but the temperature is very well recorded. Then if you could establish a relationship between these paired data sets, then you could use that relationship to model dissolved oxygen. And that's exactly what we do with another model, another example, also looking at correlation, but doing it in a little bit different way. In this case, what we're doing is once again at time zero, always at time zero. At time zero, we're going to look at both of these time series elements, and we're going to calculate its correlation factor and use that in our model to simulate. So if I just run this model like it is, and we look at a time history, and don't worry too much about the blue at the moment, just look at the red, and the red is the dissolved oxygen time history. You can see there's a lot of points missing. Also, there's an area down here where something went a little bit wrong with the gauge, and it measured these strange values over here. And so if it's determined that something was wrong here, then you'd have to throw these out. So what we could do is say, well, but we do have good temperature values during this time. In fact, most of the time we have good temperature values. Well, what if we could just establish a correlation between these two parameters and then just model the dissolved oxygen? And that's what we do here. This model requires actually using a DLL in order to calculate the correlation, because the multivariate chart, yes, it can tell you the correlation factor, but it's just a view. You just view the number. But if you actually need the values, in this case, we have a linear relationship between these two, so we can get the slope and the intercept. And with those two outputs that this DLL provides, we can then build a model to calculate dissolved oxygen from the temperature. So we put temperature and DO into there. It walks through both of these time series and calculates a correlation, slope and intercept. Then we can come over here and we can simply apply the slope and intercept factors to the temperature and calculate or estimate what the DO would be. So when you compare now if we look at the blue is the estimated dissolved oxygen given the correlation between temperature and dissolved oxygen. And you can see it's not too bad, actually. We fit pretty well to the measured dissolved oxygen. And more importantly, we're bridging the gaps in some areas where we didn't have any information or bad information. So if I zoom in over here, then especially over here in January 2018, you can see we didn't have any dissolved oxygen data for that whole period right there. So now we can run an estimate. We can calculate an estimate of dissolved oxygen that's a function of temperature over here. And then also where we have the bad data, we can just use temperature and override what we might be seeing for this bad area here. And so at the very beginning of this webinar, remember I mentioned how a linear interpolation might not always be good. If it's a longer period of time, that would be this case and this case, then doing this correlation could be useful. But it does require that you have both data sets in a time series. Okay, so the next one I want to show you is autocorrelation. Sometimes it's useful to have autocorrelation or to calculate autocorrelation in a time series. Autocorrelation is how correlated a value is at a certain point of time to the value that it was recorded on the previous time point, or some previous point in time previous to it. In our case, we're doing daily time steps, and we have daily time values in time series. So our autocorrelation will look at the previous day value, and we have again, this is a DLL that's going to calculate the autocorrelation. But you can. This is another one of those things where perhaps you need that. Maybe you need that at the beginning of your model. I don't have a submodel in this, but what you end up with here is if we look at the autocorrelation factor, you can see it starts out not very good because it needs time. It needs more values to be able to come up with a good value. But it doesn't take long before finally we get a pretty good autocorrelation factor here, in this case 0.98. So what can we do with autocorrelation? Well, what that allows us to do is to estimate or model functions like temperature in your model that might be varying over time as stochastic. And so that leads us to looking at a seasonality model. And in this model, we have a time series of temperature. And if I run the model and I just look at temperature, and I'm just going to look at one realization. If you zoom into a part of it, you'll see here that, and I should probably make this a bit longer. What you see here is that, oh, one more thing I want to do. I want to add symbols. Okay, so what you see is it's not just totally random through time. If it's running high, it'll kind of stay high. It might go low and stay low for a while, and go high and stay high, like that. That's what autocorrelation is doing. A higher autocorrelation factor will cause these points to stay in a region, a high region or a low region, longer, and so you'll have longer swings or a longer, wavelength in how they're transitioning from highs and lows. And so that's the natural system. That's how it would be in nature. And so it would be good to calculate an autocorrelation factor if you were trying to estimate the temperature in a model. And so if we're trying to do it in a model, what we could do is start out by first calculating the seasonality, or the adjust, how it adjusts over the long term. And so we ignore the noise of the daily fluctuations, and we look at just the average averages for the months. In a table view, that's not what we want to look at. But what we're doing here is we're looking at just averages over the month, so just 12 values, and then drawing a line in between those. And so that gives us the seasonality. That gives us the overall shape as it moves through the months. So once you know this, and how it might be varying from year to year, we could use this range as kind of in a stochastic. It could be used for the range of possibilities, and then we can resample every single day to get a random value between these red and blue lines, with the mean being on the green, but then put an autocorrelation in there. And so before we apply autocorrelation to the stochastic, let me just take it off. All right, so here is a stochastic that is, all it's doing is it's taking the monthly mean of the average temperature for each month we gathered that from the time series, and then also the min and the max temperatures for each month, and then we can assume that it will vary based on a triangular distribution. Now, we don't have to use triangular, but this is very convenient because you can apply min, average, and max essentially to the least possible value it could be, most likely being the mean, and then the maximum you'd ever see, and you can get that from those values. Now, if we just resample that every day, then what we end up with when we run this model is something that looks like this. And the red is the measured time series, and the green is our simulated, our estimated. And you can see how much more jagged our green values are. It looks like it's moving up and down a lot faster, and the reason for that is because we do not have any autocorrelation. We have zero autocorrelation, and so every day is just totally random from one day to the next. That's why it might be useful to use an autocorrelation factor, which we've calculated over here, and that we can apply to our stochastic. So we can come into our stochastic, click on more, autocorrelated, and then just reference the output from that DLL called autocorrelation. And now that we have that, rerun the model. And now we will have something that looks a little bit more realistic. Now, you would not expect the green to be on top of or to follow the red line. That's not the idea. The idea is that it's basically following the trend, the monthly trend, and the swings that we have from lows to highs are more reasonable in that they if it's low, it stays low for a longer period, and if it's high, it stays high. So if we zoom into here, we have some low periods that stay low. We have some high periods that stay high for a while, similar to what we have in the measured record. And so that's a way to model temperature going forward by relying on a historic time series record. Okay, and the last example that I want to show you is looking at trends. And I just want to briefly mention this. We do have some example models and also past webinars talking about mostly just trends, calculating trends going forward. But the simplest way to do it is to do a running average, and you can do that with an integrator. This running average allows you to, as the points are changing, then we're gathering these values over time and calculating an average. And so toward the end down here, then you end up with points and slopes that you could use going forward. So you could gather these slope values over here and then just apply those to calculate a model of where this would go in the future. And you can calculate slope pretty easily by just gathering the last running average, last couple of running average values, and then its previous value, and calculate the slope from that. Slope is also calculated internally in a. This is a previous value element. The slope can be calculated as rate of change here from that there. Or you can just subtract the current value from the previous value and get the slope change, and that it can be used as an input for a future projection model, not very far into the future, but it can be used for the immediate future, for modeling the immediate future. Okay, so this is all of the models, and that concludes the webinar. I realize I went through a lot of things, and submodels by themselves are already complex. So that's why I'm going to post all of these models, make them available to you so you can work with them, play with them, see if they might be useful for modeling that you might be doing in the future. All right, so at this time, I will pause here and see if there are any questions for a bit. And if not, thank you for joining, and hopefully we'll see you next week for our final lesson in the water management series. Thanks again.